Welcome. In this video, we will begin discussing the intermediate field Zeeman effect. All right, so this time we will not be able to consider either the Zeeman part or the fine structure Hamiltonian as a perturbation, but rather we now have to consider them both as the perturbation. And throughout this video, I will also solve problem 6.23 as it appears in the third edition of Griffith's Introduction to Quantum Mechanics. Okay, it's going to be solved implicitly. I will mark it in this timestamp though. I just hit my mic. So if you're here for that, make sure to check out the timestamp. All right, so intermediate field Zeeman effect. What does this mean again? As I mentioned, we now have to take our perturbation Hamiltonian to be the sum of the Zeeman part as well as the fine structure Hamiltonian. And we are going to want to apply perturbation theory to this. However, this time it won't be quite as easy as before, because now, which quantum numbers do we choose? We made different choices last time. Now it's not really that simple. So unfortunately, in this case, we will have to build our W matrix, okay? So just a quick reminder, when we have degenerate perturbation theory, we built this huge W matrix. Well, I guess the size depends on the problem. In this case, it's going to be huge. And each one of these W elements, right, W alpha beta, they were the inner product of some state alpha, or psi alpha if you want to call it that way, with our Hamiltonian and then beta. Right, so alpha is going to be state 1, and then beta 1, and then you're going to change them 1, 2, 1, 3, 1, 4, and so on, right? And we're going to build the entire matrix using this method. And that is going to take a while, so this is going to be somewhat of an annoying problem, but you know. Okay, so if we want to be able to determine the energy levels that our system is going to have in this case, right, when the strength of the Zeeman, or the field that causes the Zeeman effect, is going to be somewhat stronger, and thus we have to use intermediate field, but not quite strong for us to go to strong field. We now have to see what we want to do. So we want the energy levels, just making clear that the process here is clear for us. So we want to find the energy levels, thus we need to determine the W matrix. So what are the states? Now I went ahead and wrote them down. They are the same states that we did in a previous video. This time, of course, we are going to use different writing. Now there's a lot of things here, so let's go through it step by step. So what I wrote down here are all of our n equal 2 states, okay? Since that's the case that we are going to be dealing with, n equal 3 I will do in another video. And the nomenclature that I chose, so basically this is the notation that we chose, okay? I chose to go with the same notation that Griffiths used. So we are going to have state JMJ, and we can also write it as the tensor product of states LML and SMS. Right, so this is going to be, of course, if you want to find these exact states, there are two ways to go about it. One, you can look into a Clebsch-Gordon coefficient table and then just build them, or you can use the methods of angular momentum that we have used in the past. But of course, since that is not the topic of this video, I simply looked them up in a table and wrote them here. But these are our 8 states. 2 of them correspond to L equals 0, and the other 6 correspond to L equals 1. Okay, and it's important to keep in mind that these states, so here 1/2, 1/2, this means J 1/2, MJ 1/2, then we have 0, 0 for L equals 0 and ML equals 0, and 1/2, 1/2 for S 1/2 and MS 1/2, and the same for every single one of these states. Okay, and in this first case, of course, there's only one state, but there are some states where there exist 2. Okay, or basically it's comprised of these 2 substates. All right, so these are our 8 states. So let's begin working on our beautiful, beautiful matrix. So let's be very, very, very careful here. So I'm going to take my time and just draw this out. So we're going to have W1, 1, W2, 1, W3, 1, W4, 1, and so on and so forth. Then we have the diagonal elements, so W22, I'm gonna write this down so that I make sure that, actually, maybe I'm gonna use lines. Oop, that I meant to use this. So that's, oops, 3 spaces. So we have 8 states, so we need an 8 by 8 matrix. So 1, 2, 3, 4, 5, 6, 7. Oops. And now let's use that. So that's 4, 5. I know, I'm pressing shift, so my computer is overreacting a little bit. So that's 4, 5, 6, 7, and 8. All right. Just extend some of these lines. We just want to make sure that our matrix is as tidy as possible, because when we are dealing with such a big matrix, it's going to be really easy for things to go wrong. Oh, actually, I want my normal pencil now. There we go. So this is our W matrix. So on the diagonal, maybe I'm going to use actually a different color for the diagonal just to make sure that we can distinguish it properly. So diagonal is going to be red maybe. So W11, W22, W33, W44, W55, W66, W77, and W78. And maybe I'm gonna just get rid of these lines here that are protruding. And there we go. Okay, so what about our off-diagonal elements? Let's see. So the off-diagonal elements, actually, let me remind you what W is, just in case. So W alpha beta, this is the alpha state, inner product with the Hamiltonian and the beta state. So for example, W11 is simply the inner product, right? Or basically the expectation value in that case of H in the state 1. And if we have a W21, then alpha would be state 2 and beta would be state 1. What would happen in that case? Well, states 2 and 1, as you can see, are different states. So they are orthonormal, and thus their inner product will be 0. And in fact, that is going to be the case for basically all of the off-diagonal terms. Luckily, otherwise it would be annoying. There is, however, one thing we have to note, because there are some of these states that actually might be different states, but like 5 and 6, but they have the same substates. So that happens with 5 and 6 and 7 and 8. As you can see, this is comprised of the state 1, 0, 1, 2, 1, 2, 1, 0, 1, 2, 1, 2, or 1 half, sorry, 1 half, 1 half. And 7 and 8 also have 1 minus 1, 1 minus 1, 1 half, 1 half, 1 half, 1 half. And similarly for the other two states. So for the other two halves, I mean. So these are the only ones. So 5 and 6 and 6 and 5, of course, right? So W56 and W65, as well as W78 and W87 will be the only off-diagonal elements that will not be 0. So let's go for all others. So 0, 0, 0, 0, 0. Thank the good Lord that this is 0. Otherwise, it would be very annoying. Imagine having to do all of these. So 5, 6, and 6, 5. So let's go. This is 6, 5. 6, 5. And W, 5, 6. And then this is 0. And then this is 0. This is 0, 0. And then we have W8, 7. And W 7, 8, and everything else is also 0, 0, blah, blah, blah. Right? Because of the fact that whenever you do this product, the states alpha and beta are going to be completely orthonormal, and you're going to get 0. All right, so basically what we have to do is find all of these remaining states. So W11, 2, 2, 3, 3, blah, blah, blah. And then we have to find the eigenvalues of this matrix, because when we do that, we're going to diagonalize it, and then we're going to end up with the good states. And then we can just find the energy. I mean, those eigenvalues will be our energies, actually. Okay, so how do we begin? Well, just calculating. So W11. I wrote down here the formulas that we have found previously for the fine structure energies, as well as the formula for the Zeeman contribution. So we just have to begin. Now we can do something to make our job just a little bit easier. Let's find all possible values for the fine structure energy. And why do I want to do that? Because there's only two possible values of J. It's either, let's take a look at our states. J is either 1/2 or it's 3/2. There's no other value for J here. Mj can have different values, but J is either 1/2 or 3/2. So when we calculate the 8 states, we don't want to calculate this thing 8 times. So let's calculate it twice, and then we just plug in the corresponding value. So the fine structure formula, what is it? First, we have this E2 squared. Now we know that E2 is simply E1 over n squared, which in this case is 2 squared, so 4. And of course, this is squared. And this is multiplied by 1 over 2mc squared times 3 minus 8 over, okay, and now J. So which value of J do we want to do first? Maybe 1/2, and then we will do 3/2. So for J equals 1/2, the denominator here would be 1. So this would be simply 3 minus 8, which is of course minus 5. So let's rewrite this as minus 5. Okay, and well, in principle, this is already done. So you could just leave it like this. However, just to follow the convention that Griffiths does, what we'll do here is that we will rename some of these constants using the fine structure constant. So we will plug in for one of these E1s, considering that it is squared, so you got 2 basically, so you have E1 times that. So one of these E1s we will take to be minus 13.6 electron volts, right? And then you have the other one we will take to be what we find from here. So from here we will say, all right, alpha squared, because we have 1 over 2mc squared and E1. So let's actually solve for E1 over 2mc squared. So E1 over 2mc squared, right? So in order for us to do that, we would have to divide by 2 both sides. So we would have that this is minus alpha squared over 4. All right, so we used one of our E1s as minus 13.6 electron volts, and the other one we used to, instead of having E1 over 2mc squared, we now have minus alpha squared over 4. So times minus alpha squared over 4. All right, so that's gone, that's gone. I almost forgot about my 4 squared, which is a 16. All right, and then times minus 5. So all of this is going to be, well, the minus, these 2 minus signs cancel out. We end up with minus, and then we have 13.6 electron volts over 64 times alpha squared times 5. And since this 5 came from the part that depends from J, from this right here, and all of this did not depend on J at all, right? This simply came from here. Then this part right here we will call gamma, right? To use the same notation as Griffiths. So this we can simply write, except for this minus sign, by the way, this came from 5. So this would be minus 5 gamma. Okay, amazing. So that is the case for J equals 1/2. So what about J equals 3/2? So maybe I'm gonna keep it, but like this. So this is gamma. All right, so for J equals 3/2, we get that the fine structure energy is going to be, well, the same gamma at the front, right? All of this is going to be gamma. In principle, you could have just called this gamma right away, but I wanted to use the same notation that Griffiths did. That's why I did it like this. And then we have 3 minus 8 over 3/2 plus 1/2, which is 4/2, which is 2. So we have 3 minus 4. So this is minus gamma. All right. So now we rewrote this and we won't have to be calculating the fine structure energy over and over. We simply see what the value for J is in each state and we plug in the corresponding result. So it's either going to be minus 5 gamma or gamma. All right, so let's now finally go for the first state. So W11. So this is state 1 and then our Hamiltonian, which is fine structure plus Zeeman contribution, state 1. Okay, this is going to be, we can of course separate these two, so we get the expectation value. Actually, no, I'm going to keep it like this so that we are explicit in the fact that we are doing this expectation value with respect to state number 1, plus expectation value of the Zeeman contribution. And of course, the Hamiltonian acting on our state is going to be the same as our energy acting on the state. This part we don't know yet, so I'm going to leave it like this. And we already know what happens here. So what is the energy? The energy is simply a number, so we can pull it out. So we pull it out of the inner product. And then we have this orthonormal state, which inner product is going to be 1, so no need to write it down. And state number 1, it had J equals 1/2. So what was the energy for J equals 1/2? It was minus 5 gamma. So instead of writing the energy, now actually maybe I'll write it down here. It's going to be minus 5 gamma. All right, plus. And now we need to see what's up with this Hamiltonian. So the Hamiltonian was the following. It was, wait, I'm supposed to write a 1 in there. It was supposed to, it was E over 2m times the external field times LZ plus, I think it was 2SZ. And I'm gonna just double check. Making a mistake here would be unnecessary. Yeah, that's it. Okay, so what are the operators LZ and SZ acting on state 1? Well, that's simply going to give us H bar ML and H bar MS. So we can take an H bar out. So we get H bar E over 2m times the external field. And then we get ML plus 2 times MS. Quite similar to something we have done in the past. And now all of these are simply numbers. We can pull them out, right? So we get, well, minus 5 gamma plus H bar E over 2m external field times ML plus 2ms. And then we get the inner product of 1 and 1, right? Which is simply 1. And we can see now that we have this thing right here, which is going to be the same every single time. The only part that changes when we go to a different state is going to be this. So we can just call this something like beta, right? I'm going to use the same notation that Griffiths used, so that in case you are following that book, you can, know what to do. All right, so this is the part from Zeeman, and thus W11 is going to be minus 5 gamma plus beta. So let's now go into our table here, into our matrix actually, and write it down. So this is minus 5 gamma plus beta. And now if you are following the Griffiths book, then you might notice that the signs are changed. So in Griffiths book, every single element I write in this matrix is going to have a minus outside of it. And that is simply a convention that Griffiths used because it's going to save us a little bit of trouble later on, because basically everything will have a lot of minus signs here. So adding a minus sign makes it cleaner. So that's just in case you notice that difference. I will not use that because I always like to do an approach where it's basically like if you didn't know that. So we're just going to go straight ahead and we will get the exact same result. All right, so we got W11. So let's get rid of this and go for W22. So W22. This is going to be exactly the same, but this time for state 2. So what is state 2? State 2 has J equals 1/2. So we already know the first part, right? The energy, the fine structure energy, because we know this is fine structure energy, plus the Zeeman part. And the Zeeman energy. So the final structure we already know is going to be minus 5 gamma. And the Zeeman part is beta times ml plus 2ms. So what are L and ml and ms? All right. So wait, did I explain it properly when I did the last state? So in the last state, ml, yeah, I don't think I explained it much. I apologize. ml was 0 and ms was 1/2. That's why we did 2 times 1/2 and we got 1, which is why I wrote down beta. I don't think I explained that properly. My apologies. Now ml is 0, so that part is still 0, but now ms is minus 1/2. So when we multiply by 2, we are going to get minus 1. So this here is 0, and this is minus 1. So in the end, we get minus 5 gamma minus beta. All right, let's plug it into the matrix here. So minus 5 gamma minus beta. Let's now go for W33. Maybe here. So W33. So this is going to be the, again, fine structure energy plus Zeeman part. So what is the fine structure part? Let's go and check out our state. We are in this one. So this time it is state with J equal 3/2, which means we have to take the energy to be minus gamma. So this is minus gamma. And then we have plus the Zeeman contribution, which is plus beta times ml plus 2ms. What are ml and ms? So ml is 1, ms is 1/2. So we get 1 plus 2 times 1/2. So 1 plus 1, 2. So we get, actually, maybe like this. I'm just going to write 2 immediately. So plus 2 beta. Let's plug it in. So this is minus gamma plus 2 beta. Time for W44. Let's change colors. W44. This is, well, let's see, what is the fine structure energy? So this has a J of 3/2. So it's going to be minus gamma. And then the Zeeman contribution is going to be beta times ml plus 2ms. What are those values for this state? So state 4, ml is minus 1, ms is minus 1/2. So we get minus 1, so minus 2. So our state is going to be minus gamma minus 2 beta. Let's now plug it in. So minus gamma minus 2 beta. Now let's go for W55. So W55. What is this state? So this one has J equals 3/2 as well. So we can also just go ahead and write minus gamma. What about the Zeeman contribution? So beta times. What are ml and ms? So now, as you can see, oh, it's actually not quite that simple anymore. Now we have 2 states. Now it would be possible to do it like I just did, but let's take a step back, right? Because this time we have all of these things. So it's going to be important to do this carefully, since we will have to do it again in the off-diagonal terms, and there you might get confused. So I'm just going to copy our state number 5. Actually, maybe copy all that. Whoops. Okay. And I'll actually go to a new page. So let's now work on, wait. Yeah, I updated my software and it's really been buggy after I did that. Okay. So this is our state number 5. And we want to determine W55, which, as you know, is bra of state 5, our perturbation Hamiltonian, and then our ket. So let's do this step by step. So bra of 5 would be bra of this. So we get square root of 2/3, right? We have real numbers, so no need to worry about the complex part. Then we get 1, 0. 1/2, 1/2, plus square root of 1/3, 1, 1, 1/2 minus 1/2. All right, and so this was the bra. Now comes the Hamiltonian. So Hamiltonian fine structure, Hamiltonian from Zeeman. Well, now times, I'm gonna continue here. And now we get actually the exact same thing, so maybe let's just copy it. All right. So now we have to do this product. So first of all, let's allow our Hamiltonian to act on state 5. We want this to act on each one of these things. Now, all of these have j equals 3/2. So the fine structure part will actually be the same, right? It's going to be minus 5. Okay, I forgot. I need to check. So for, where was it? Wait, here, sorry. So for 3/2, it's minus gamma. Okay. So this is going to be minus gamma. And then we have the Zeeman contribution, which is going to be beta ml plus 2ms. Now remember, this is L, ml, s, ms, and the same here. So if we now determine that, this is for the first part, right? So actually, maybe we should multiply through just to make sure that this is completely clear. So because this is going to be acting on two parts. Yeah, actually, let me take a step back just to make sure this is as clear as possible. So this is going to be, so we had this, fs plus hz. I'm gonna use another line just to make sure that this is like super clear, because this is where you might get confused. Okay. So now we get the fine structure Hamiltonian times this first part. So square root of 2/3, 1, 0, 1/2, 1/2. And then we get plus the fine structure Hamiltonian times the other one. So square root of 1/3, 1, 1, 1/2 minus 1/2. And I'm running out of space here, but I'm gonna continue downstairs. So now we get Zeeman Hamiltonian times the first part. So square root of 2/3, 1, 0, 1/2, 1/2, plus the Zeeman part times square root of 1/3, 1, 1, 1/2, and then we have minus 1/2. Yes. All right. So this is what we are now dealing with. So let's go to a new page. I'm gonna put it right there. Okay. So now we have to multiply through. However, we will save ourselves a few steps, because we know that if we multiply this state with this one, right, the two ones that are different, we're going to get 0 because they are orthonormal. And the same if we multiply this one with this or this. So we are only going to write down those that will not be 0. So let's begin with this times this. So if we do that, we are going to get square root, actually we get square root of 2/3 squared. So we get 2/3. So we get 2/3, 1, 0. Oh, this is supposed to be like that. 1/2, 1/2, and same here. Sorry. And then we get fine structure Hamiltonian, and then 1, 0, 1/2, 1/2. I think my nomenclature might look a little bit weird here, but I hope you get the gist. All right. Then we get this part, which is 0. And this part right here comes next. So then we have plus, this is again 2/3. So 2/3, 1 0, 1 2, or 1/2. Why did I say it like that? 1/2. The Zeeman contribution, 1 0, 1/2, 1/2. And then we have this part multiplying. So we get this times this. So we get 1/3. So plus 1/3, 1 1, 1/2 minus 1/2. Then we get the fine structure Hamiltonian. Then 1 1, 1/2 minus 1/2. And then plus this times this part right there. So we get 1/3 and 1 1, 1/2 minus 1/2. The Zeeman Hamiltonian, I don't know why I put parentheses, I'm going to take him out. 1 1, 1/2 minus 1/2. Okay. So now we have the Hamiltonians acting on the states, and we already know what that is. So fine structure acting on these states, which have j equals j equals 3/2. That means that this is going to be minus gamma. So our fine structure, actually I'm going to use a different color, maybe white. Yeah. So minus gamma, minus gamma. What about the Zeeman part? Well, this is Zeeman, and here we have ML and ms. So this is going to be beta times ml, which is 0, plus 2 times 1/2. So this is simply going to be beta. So beta. Then this part right here. So this is going to be beta times, and now ml is 1, but now ms is minus 1/2. So we get 1 minus 1, so 0. So 0, and all of this is gone. All right, what else? Then we have, actually we already did that. So the final step is to take our constants outside and see that all of these states are orthonormal, which means that we're going to get minus 2/3 gamma from this part, and the bras and kets will cancel each other out. They will be 1 because they are normalized. Then from this we get plus 2 beta over 3. From this part, we get minus gamma over 3. So if we add this up, we get minus gamma plus 2 beta over 3. All right, so you could have actually done a lot of this like mentally, but I wanted to do this procedure once in an easy case, because we will now have to use it in the off-diagonal terms, and that can be a little bit more confusing, not too much, but a little bit more, so I wanted us to be familiar with the process. All right, so let's plug this into the table. So minus gamma plus 2 beta over 3. So minus gamma. So minus gamma plus 2 beta over 3. So let's now go with W56 for example. Let me use the same page per. Actually, no, it's no way I use the same page. A different one then. Let me go for states 5 and 6. So these ones. 5 and 6. There we go. Okay, so W56. The good thing is that W56, as we saw when we were first seeing degenerate perturbation theory, W56 is actually the same as W65. So we will actually only have to find one of these. So whichever one you want to go for, doesn't matter. Let's go for W56. And we're going to do exactly the same thing that we just did. So we'll have left side will be, let me do this step by step. So this means bra of 5, Hamiltonian fine structure plus Zeeman, times this. And actually, maybe it would have been even a bit clearer if I had multiplied here. So we get 5 Hamiltonian for the fine structure, 6 plus 5 Zeeman 6. Yeah, I think that would have actually been maybe clearer. Well, let's do it like this now. Maybe it is better. You guys can let me know. Okay, so bra of 5, it's going to be square root of 2 over 3, and bra of this, so bra of 1, 0, 1 half, 1 half. Then we have plus square root of 1 over 3, 1, 1, 1 half minus 1 half. And then comes, actually, now I have to write a lot more, I think. Well, it doesn't matter. Then we have a fine structure Hamiltonian times square root of 1 over 3. So actually, if we are multiplying by square root of 1 over 3, it means that the 3 downstairs will be 3 squared. So we get rid of the square root. So this is actually square root of 2 over 3. Okay. So here we still need, okay, so now we go into this part, right? Actually, wait. Something here is a, wait. There we go, sorry. My parenthesis was off and it confused me. All right, there we go. I didn't, okay, sorry. Let's continue. So let's now go for state 6. So this is going to be minus square root of 1 over 3, 1, 0, 1 half, 1 half. A little bit short on space, but I think I can manage. And then we have plus square root of 2 over 3, 1, 1, 1 half. Oh, I can't go any further than that, but I think I can do minus 1 half. All right. So now that's just the first one. So actually I can just copy this, right? I can just copy and paste it and just change the Hamiltonian. Yeah, okay, that's a good idea. So I'm just gonna write down the other Hamiltonian. So we are adding these two together, and this is going to have the Zeeman Hamiltonian. So of course, the fine structure will now act on each one of these, and we will get, well, quite a few states. So let's do exactly that. So it gets a little bit annoying now, I'm going to admit, but we have to do it. So let's multiply this state times the Hamiltonian times this one. And of course, we will also multiply by this part, but that part will be 0 because the states are different. Okay, so we get square root of 2 over 3 times minus square root of 1 over 3. So we get minus square root of 2 divided by 3. And then we get the states 1, 0, 1 half, 1 half, and then the Hamiltonian for the fine structure. What is the J of state 6? J of state 6. That is 1 half, so it's minus 5 gamma. So here we get minus 5 gamma times the same state. 1, 0, 1 half, 1 half. So let's actually go forward now. We take the minus 5 gamma outside, and we then have the inner product of the state with itself, which is going to be 1. So we can actually write this first part as plus square root of 2, square root of 2 over 3 times 5 gamma. The minus signs cancel out. So that comes from this times this. As I mentioned, this part will be 0, so now we need this part times the first. I'm gonna get rid of some of these lines. All right, so let's change colors. We get plus, let's see, actually this one is 0, so we have to go for this. We get plus square root of 2 over 3, and then we get state 1, 1, 1 half minus 1 half. Then we have the Hamiltonian for the fine structure acting on a state which has a J of 1 half, which means it's minus 5 gamma. Oh, what was that? Minus 5 gamma. And then 1, 1, 1 half, minus 1 half. All right, so again, we can pull out the minus 5, and we will have the inner product of a state with itself. So that's going to be 1. And finally, we are left with minus 5 gamma. So we get minus this times 5 gamma. So we can actually see that at least these two contributions are canceling each other out. Now, and notice that if we had done W65 instead of 56, we would have gotten a different value of gamma, right? Minus gamma instead of minus 5 gamma, but they would still have canceled each other out. That's why you can see it doesn't matter which one you choose. Let's continue now with this. So we get this part multiplying this. So this is going to be minus square root of 2 over 3. And then we have 1, 0, 1, 2, 1, 2. The Zeeman Hamiltonian acting on this state, which is going to be beta times ml, which is 0, times 2 times 1/2. So we get 1. So it's just beta. And then we have 1, 0, 1/2, 1/2. So of course we can now pull the beta out, and we'll have, once again, the inner product of a state with itself. And since it's normalized, it's going to be 0. So we'll simply have minus square root of 2 over 3 beta. And finally, we need this part right here. So let's multiply. Whoops. And then we get plus square root of 2 over 3. And, well, state 1, 1, 1/2 minus 1/2. Then we have the Zeeman Hamiltonian acting on this state, which is going to be beta times ml, which is 1, plus 2 times ms, which is minus 1/2. So we get 1 minus 1, which is 0. So this entire thing here is also 0. So what is our result? We get that W56, which is the same as W65, is minus square root of 2 over 3 beta, right? This part right here, which is the only one that survived. Okay. We are nearing our objective. So this is minus square root of 2 over 3 beta minus square root of 2 over 3 beta. Okay, W66. Let's go. Okay, what was state number 6 again? This. Wait, what's happening? There. Hopefully I copied it correctly. Looks good enough. Okay, so W66. So we have to take the inner product of this part with itself, which is going to be something we have already done. So let's maybe speed it up a little bit. So what we will have is this part right here. So W66, right? So 6 Fs plus Hz6. And this will be, well, the bra of this times fine structure Hamiltonian times the ket. So we get minus square root of this, 1, 0. Then we get 1/2, 1/2. And then I'm thinking if I should multiply through right away, but I think we can just do it later. I'm going to write it like this once, and then we can go a little bit faster when we are multiplying, I think. And then we get Hamiltonian for fine structure, Hamiltonian for Z. And then this will act on this part right here. Right, so that is going to be multiplying all of this. Okay, so let's now do the multiplication. So we will have this part times the Hamiltonian times the first part, right? Because the second one will be 0, so we only have to consider this. So when we do that, the minus signs cancel out. We get 1/3 of the value of the energy for the fine structure. And what is that going to be? I don't know. What is the J for this one? State 6 has J 1/2, which means energy of minus 5 gamma. So this is minus 5 gamma. And then we get this term, which we now must multiply. Actually, we didn't multiply by the Zeeman part, so let's do that first. So let's multiply now this times Zeeman. So there we get plus 1/3 beta times ml, which is going to be 0. Wait, which one are you? No, we're using, it's 0. So 0 plus 2 times 1. So it's simply beta. Okay, I'm just doing exactly the same as before, but speeding up a little bit. And then we do get the second term. So let's get rid of this. And now comes this part times the fine structure times this part right here. So we get 2/3. What is the fine structure energy? It's once again minus 5 gamma. And then we get this times this, the Zeeman part. And that's going to be 2/3. And Zeeman, that's going to be beta ml plus 2 ms. So ml, what is it? It's 1. 2 ms, it's minus 1. So this part actually is going to be 0. So here we get 1/3, 2/3 of minus 5 gamma. So we get minus 5 gamma plus beta over 3. All right, now let's plug it in. So minus 5 gamma, whoop, that's W77. That's minus 5 gamma plus beta over 3. All right, time for W77. So let's go ahead, copy state number 7. Somehow without copying the other ones. There we go. Okay, so this is state 7. All right, so W77, let's do it in the exact same way. So we get square root of 1/3, 1 minus 1, 1/2, 1/2, plus square root of 2/3, 1 0, 1/2, minus 1/2. Then comes the Hamiltonian, fine structure and Zeeman. And now this is going to be multiplying by this exact same thing. Okay, so now let's begin multiplying. So I'm going to do exactly the same. So this part times this. What do we get? We get, well, and of course, times this part, right? We have to multiply by the one that has the same quantum numbers, and because it's got to be the same state. So we get 1/3 and fine structure of what's our value of j here. So in state 7, we have value of j 3/2, which I believe is minus gamma, right? Yes. So the energy is minus gamma. Then we get this times the fine structure part, where we get 1/3 beta. And what is ml? It's minus 1, and ms is 1/2. So we get minus 1 plus 1, 0. All right, next part. Then we have, actually, let me get rid of these lines. Let's change color. So we get this times the fine structure. So that's going to be plus square root of 2/3 squared. So we get 2/3. And then we have the fine structure part, which is going to be, again, minus gamma. And then Zeeman, which will be 2/3 beta. And ml is 0. ms is minus 1/2. So we actually get a minus 1. So this is going to be minus 2/3. So if we now add this up, we get that W77 is going to be minus gamma, 1/3 plus 2/3 is just 1, minus 2/3 beta. All right, so minus gamma minus 2/3 beta. Minus gamma minus 2/3 beta. W88 comes next. I guess we could do 87, 78. Doesn't matter. So let's go for 88 because I already said it. And you know, no takesy backsies. Okay. Great. So let's do the exact same thing. So W88. Maybe this time we can do it mentally, right? So we want to do this times the find structure Hamiltonian, which, what's the value of j? It's 1/2. So that means it's going to be minus 5 gamma. So we get this part squared, so we get 2/3 times minus 5 gamma. Then this part multiplies the Zeeman Hamiltonian and then the other part of this. So we get plus 2/3 beta ml, which is minus 1, plus 2 times ms, which is 1, so 0. All right, now this multiplies the Hamiltonian, so we get 1/3 squared, so we get 1/3. Right, I'm doing exactly the same thing as before. If you are not sure, you can just write it in the same way I did before. 1/3 times the Zeeman, so the fine structure part, sorry, minus 5 gamma. And now comes the Zeeman part, so we get 1/3 beta, ml is 0, and 2 times minus 1/2 is minus 1, so we just get a minus sign here. So if we now add this up, we get minus 5 gamma minus beta over 3. So let's go ahead and plug it in our little matrix. Minus 5 gamma. Wait, why can't I go back? I think it froze. Yes. I'm going to have to edit this out. All right, I fixed it. So we wanted to plug this value in. So minus 5 gamma minus beta over 3, I believe. Actually, I already forgot. I should double check. But let's see. Minus 5 gamma minus beta over 3. Let me double check. Minus 5 gamma. Yes. All right. So the last one that we have to find is W78 and W87. So let's do that immediately. All right. So to do that, I'll once again do every step because this might be a little bit more confusing. So W78, which is the same as 87, this is going to be the bra of 7. So we get square root of 1/3, bra 1 minus 1, 1/2, 1/2. You can see here how this bra and ket notation is super handy, right? We only need to understand the states we are dealing with. We don't really need to write them down. And then we get plus square root of 2 over 3, 1, 0, 1/2 minus 1/2. And then we get the Hamiltonians. And now we multiply by this exact thing here. All right. So when we do this, we're going to get this first part times the Hamiltonian, which will be acting on these states. And of course, this, when multiplied by this state, will be 0 since they have different quantum numbers, not the same state. So now the only part that will remain is when it is multiplied by this part. So we will get square root of 1/3 times square root of minus 2/3. So we get minus square root of 2 over 3. And then we have the Zeeman part, sorry, not the Zeeman, the fine structure part for this state. What is the value of j for the 8th state? It is 1/2. So that means it is minus 5 gamma. So minus 5 gamma. And then we have the inner product of a state with itself, which is 1. All right, then we have the next product, which is the Zeeman contribution. Once again, it's going to be with the same state, so we get minus square root of 2 over 3. And then we got the Zeeman part, which is beta, ml, which is minus 1, plus 2 times 1/2, so 1. So we get minus 1 plus 1, 0. All right, now let's go for the next set of multiplications. So we get this part times the fine structure and then times this. So we get plus square root of 2 over 3 times the Zeeman of this. Why do I say Zeeman? The fine structure part. Since J is 1/2, that's minus 5 gamma. And as before, this and this cancel out. This is positive, this is negative. And that, of course, makes sense because we need W78 and W87 to be the same. That's what allows it. All right, then we multiply this with this. And in that case, we get plus square root of 2 over 3 times beta times ml, which is 0, times 2 times minus 1/2. So we get a minus 1. So W78, which is the same as W87, this is going to be minus square root of 2/3. Let's plug it in. All right, so minus square root of 2/3 beta. Minus square root of 2/3 beta. We have now completed our matrix, but we are not free. We can now breathe, but we are not free. Because this was only step 1. Right? Now we should take a moment to appreciate how nice it is whenever we can actually guess the correct states, right? It is nice. Okay, so what do we want to do next? Now we want to diagonalize this. So we want to take this matrix, the W matrix, and subtract the identity times lambda. And this, we want the determinant of that to be equal to 0. Right, so we can find the eigenvalues. That's what we're going to do now. So yeah, I need to add a minus lambda, but there's no way I can fit it in here. So I have to go to a new page and redo this. Okay, I'm gonna just do it quickly. So, okay, so here I have rewritten our matrix, but this time considering that this is W minus the identity times lambda. And of course, now we want to take the determinant of this and we want to set that equal to 0. So that way we will find the eigenvalues, which will in turn be the energies. All right, so that's what we want to do. So we have to take the determinant of this 8 by 8 matrix. You might remember how to do that. It is going to be somewhat annoying, but not too difficult. So what we have to do here is we take the first element, we then cover the row, the column and the row, and then we multiply by the determinant of what is inside. And the determinant of what is inside is this thing times the determinant of what is inside, which is this thing times the determinant of what is inside, which is this thing times the determinant of this 4 by 4 matrix. So basically, we get these 4 terms multiplying each other times the determinant of the 4 by 4 matrix. So let's go step by step. Let's get rid of that. And that would be minus 5 gamma plus beta minus lambda, that's the first part, times minus 5 gamma minus beta minus lambda, that's the second one, times minus gamma plus 2 beta minus lambda, that's number 3, and 4 is minus gamma minus 2 beta minus lambda. And then we have to multiply by the determinant of the 4 by 4 matrix, so 4 by 4. So what is that thing? Let me now just sketch the 4 by 4 matrix. So that would be gamma minus 2/3 beta, minus gamma plus 2/3 beta. Then we have minus square root of 2 over 3 beta, 0, 0, minus square root of 2 over 3 beta. Then we have minus 5 gamma plus beta over 3, 0, 0, 0, 0, minus gamma minus lambda, by the way. Don't forget about the minus lambdas. Minus 2/3 beta minus lambda minus square root of 2 over 3 beta minus 5 gamma minus beta thirds minus lambda minus square root of 2/3 beta, 0, 0. So we have to find this determinant. All right. So how do we do that? Well, we have to take this first element, so minus gamma plus 2/3 beta minus lambda, and then we cover this, and we take the determinant of what is inside, which is going to be minus 5 gamma plus beta thirds minus lambda times the determinant of this 2x2 matrix, which is going to be the product of minus gamma. Actually, I think I'm going to have a problem with my space, but it's okay. Minus gamma minus 2/3 beta minus lambda times this part, which is minus 5 gamma minus beta thirds minus lambda minus this times this. So we get another 2 minus, which cancel each other out, and we get 2/9 beta squared. Okay, and then we get minus, right? By the way, this is determinant 4/4, just to make sure. And then we get minus, let's change colors, this part, and this time we cover this and this. So we get this times this determinant of the 2x2 matrix, which will be the same as before. Okay, so we get the minus 2/9 beta squared, and then we have this 2x2 determinant, which is the bracket part in here. So I'm just going to be lazy and write it as the bracket part. So let me now copy this and take it to a next page so that we can then rewrite this and simplify it. So, and actually by simplify, I mean factor out. So both of these parts have this brackety part. So this minus gamma minus 2/3 beta minus lambda minus 5 gamma minus beta over 3 minus lambda, and then minus 2/9 beta squared. So then this is the common part. So let's multiply by the rest. So that's the product of these two things, which is minus gamma plus 2/3 beta minus lambda minus 4 gamma plus beta thirds minus lambda minus 2/9 beta squared. Actually, that parenthesis, this one shouldn't be there. Okay, so this is what the determinant of the 4x4 matrix looks like. So now let me plug it in to the complete equation that we have to solve. So let me try to find it again. So I'm missing this part, so let me copy it. So the complete equation is this. So this times what is down here, this has to be equal to 0. And this looks quite horrible, but in fact, it isn't that bad. So as you see, most of these are simply terms in brackets, and this is a product within many parts. So if you want it all to be 0, then this has to be 0, or 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 this has to be 0. So we have to take each one of these cases separately. So lambda 1, for example, would be for this part, would be simply minus 5 gamma plus beta. There we go, that's the first value. Then we have lambda 2, which would be minus 5 gamma minus beta. There we go. We have considered both of these. Lambda 3 would be minus gamma plus 2 beta. Lambda 4 would be minus gamma minus 2 beta. There we go. Now we need to take each one of these brackety terms into consideration. Now, let's take any one of these, for example, the first one. So let's just copy it, go to a new page, and see what condition this gives us for lambda. So basically, what are the eigenvalues that correspond to this part? So we know, of course, that this has to be 0. So let's multiply through. We get 5 gamma squared. Then we get plus gamma beta over 3 plus gamma lambda. Then we get plus 10 beta gamma over 3 plus 2 beta squared over 9 plus 2 lambda over 3 times beta. Almost forgot about that. So this times that. Then we get plus 5 lambda gamma plus beta lambda over 3 plus lambda squared minus 2 over 9 beta squared equal to 0. So with this, we can now simplify a little bit. So this part cancels out this, and then we can add some things. So, well, the 5 gamma squared is going to remain. Then we have beta gamma over 3, and we have, let's see, beta gamma, beta gamma, beta gamma. There we go. So we get plus 11 beta gamma over 3. Then we have 2/3 beta lambda and 1/3 beta lambda. So we get beta lambda. And then we have 5 lambda gamma and gamma lambda. So we get 6 lambda gamma. Wait, what did I just do? Lambda gamma, there we go. And lambda squared, don't forget about that. So this has to be 0. Now this is simply a quadratic equation which we can rearrange like this. So lambda squared plus lambda factor of 6 gamma plus, what else do we have? 6 gamma, plus beta. And then without lambda, we have 5 gamma squared plus 11 beta gamma over 3. So now we simply have to apply the quadratic formula to this right here. So let's do that. And what will we get? So we get lambda has to be equal to minus b. So we get minus 6 gamma minus beta plus or minus the square root of b squared. So that would be 36 gamma squared plus 2 times the product of both. So 12 gamma beta plus beta squared. And then we get minus 4 times this. So minus 20 gamma squared minus 44 beta gamma over 3, and all of this divided by 2. All right, so lambda, now let's simplify a little bit. We get minus 6 gamma minus beta. Actually, let's divide through by 2. Let's do it later. So plus or minus. Here inside, we get 36 gamma squared minus 20, so 16 gamma squared. Then we have gamma beta, 12 minus 44 over 3. So we can multiply by 3, divide by 3, right? Minimum common denominator. So this would be 36 minus 44. So we get minus 8 beta gamma over 3. And then we have beta squared. And all of this divided by 2. We can now factor out 4 from inside the square root so that we can then simplify with this 2. So we get minus 3 gamma, simplifying with this, minus beta divided by 2, plus or minus square root of 4 gamma squared minus 2 beta gamma over 3 plus beta squared over 4. But we factorized 4 from inside the square root, which took a 2 outside, which canceled out this 2. So these are now 2 solutions, right? So we might as well call them like 5 and 6. And we can now go back quickly to what we had, and we solved this first part. But notice that the second one is exactly the same, except that every beta has a minus sign in front, right? This one also, but it's squared, so it cancels out. So that means that our result, if you want, you can go ahead and do it, but our result is going to be exactly the same, but with a minus in front of every beta. So lambda 7 and 8, we can find it immediately. It's going to be the same, but with a minus sign in front of every single beta. And that way we don't have to do, this process again. Plus, because it's squared. All right, so these are the energies that we are looking for. So our values of lambda, which are, okay, so here we go. So our energies, what are they? Actually, yeah, let me just write them all together somewhere. So, for example, energy 1 would be the base energy, which would be minus 13.6 electron volts, right? The Bohr energy, n squared. In this case, n is 2, so this would be divided by 4, plus now what we just found. So that would be, in this case, minus 5 gamma plus beta. And then the energy for the second energy would be the same thing, right? So the same, minus 5 gamma minus beta. And then the third energy, this same thing, but with lambda 3, minus gamma plus 2 beta. And then 4 would be same thing, minus gamma minus 2 beta. And then we need to go to these two. And then, well, you can see these equations. So our energies, wait, where was I writing them down? Here. So E5 would be the same thing, but plus lambda 5. This would be the same thing plus lambda 6. E7 would be the same thing plus lambda 7. And E8 would be the same thing plus lambda 8. And there we go. We just found all of the energy levels that we needed, that we wanted. And yeah, it was quite a task, but we did it. So if you got to the end, thank you very much for watching. If you enjoyed the content, please make sure to share it with your classmates, with anybody else who might find this useful. And of course, subscribe to the channel. It doesn't cost you anything, but it really, really helps me out a lot. So I'll see you in the next video. Thank you very much for watching.